So Cartesian or scalar equation of a line. Okay, the Cartesian or scalar equation of a line is written like this: ax plus by plus c equals 0. We know this from grade 9 as the standard form of a line. So we're now going to call it the Cartesian or scalar equation of a line. Okay, and a, b, and c are supposed to be integer values, where a is supposed to be positive. We're not going to be that sticky on it. It just needs to be in this form. Okay. Now, so we're going to take a look at a few lines. So in slope-intercept form, we've got these three lines here. So y equals negative 3x plus 2, 2x plus 7, and 2/3 x plus 5. With these three lines, we can tell exactly what a direction vector would be for them by looking at the slope. So in this one, the slope is negative 3 over 1. So 1 comma negative 3 is the slope. This is 2 over 1. 1 comma 2 is the direction vector. And 2 over 3, so 3 comma 2 would be the direction vector. In the first one, we could rearrange that into standard form or Cartesian form by bringing everything from the right side to the left. We get 3x plus y minus 2 equals 0. And in this case, a equals 3, b equals 1, and c equals negative 2. Okay, so same thing for the other two lines. You can put them into that Cartesian form by rearranging. A is negative 2, b is 1, and c is negative 7 for this one. Okay, and in this one, when you rearrange it, you end up with a fraction in it. Well, you can just multiply everything out to get that fraction out. Okay, and you have negative 2x plus 3y minus 15 equals 0. Now, when we look at all of these, and we look at the vectors that are parallel to them, we want to figure out how that relates to a, b, and c. Well, if you look closely, the a value always tends to be the negative of the a value always tends to be the y-coordinate of the direction vector. So negative 3 is there, negative of negative 2 is there, negative of negative 2 is there. And then the x-coordinates tend to be the coefficients of the y. 1, 1, 3. 1, 1, 3. Okay, so we're going to take a look at something that is going to be a reminder for you, hopefully. Okay, so we can look at this now and say that basically the direction vector is b comma negative a. Okay, so from standard form, you take the b, it's the x-coordinate, negative a is the y-coordinate. That gives you a direction vector for the line. Okay, now a little aside here, a bit of a reminder of stuff. Thinking of dot product, a vector perpendicular to xy is negative y comma x. So basically flipping the two coordinates and making one the opposite sign. Or y negative x works. Okay, so 2, 3 is perpendicular to negative 3, 2, since their dot product is 0. So you flip the two so that when you multiply them using the dot product, you get the same number. You change the sign of 1 so that they're the opposite numbers, they're opposite ones, so like negative 6 and 6, and it gives you 0. Okay, so since that's the case, so a vector that is perpendicular to a line or a plane is called a normal vector. So we're going to call a vector that's perpendicular to a line or a plane the normal vector. Okay, another word for that is orthogonal. Okay, and that normal vector is going to be represented by an n with a vector sign over top of it. So if m is b negative a, which we set up here earlier, m is b negative a that we saw, then n is going to be ab. So ab would represent a perpendicular vector to the line, normal vector to the line. Okay, so a proof on this is very straightforward. Okay, so let's prove that for any line ax plus by plus c equals 0, that n equal to a comma b is going to be perpendicular to that line. Okay, so let's start by let p be any point on the line. So say you've got a line like this, and P represents any point on the line. Okay? So it could be anywhere in there. P x naught y naught is a fixed point on the line. Okay, so a fixed point on the line, P naught. Okay, something that we know the values to. This one is going to be called x, y. We don't know the values to, but we are going to be able to calculate them. Okay, and then let n, conveniently called the vector AB, be perpendicular, normal to the line. Okay, so n is perpendicular to the line. If n is perpendicular to the line, then it might go something like this. Okay, there's n. The vector p naught p, so from here to here, is a vector that is perpendicular to n. Okay, so that's p naught p. Okay, so you got n going down this way, p naught p going this way. Those two are perpendicular. What do we know about perpendicular vectors? Their dot product is 0. Okay, so n dot p naught p equals 0. P naught p is this, so it's OP minus OP naught. Okay, and now we get this dot product here, where it's AB dot x minus x naught, y minus y naught. Multiply that out. We're just getting this, putting a sum between them. Multiply that out, and we've now got this expression here. AX and BY are the variable terms, x and y. X naught and y naught are known. Remember, we fixed that. We know those values. So A times x naught, B times y naught is going to be some known value. So we rearrange this so that we get this. Okay, so AX plus BY plus this ugly piece here. Except this ugly piece is going to be a constant value. When we know all the numbers, we can multiply them and add them. Let's call them C. Let's call it C. So we get AX plus BY plus C equals 0. And we said that AB was perpendicular to the line, and they end up in the right spot. Okay, so that's that formula proven. And so we're going to take a look at an example here. So let's take a look at these lines. So compare the following 3 lines. Okay, so if you want to pause the video and do what you can to compare them, and then come back in, that's great. So these 3 lines, 1, 2, and 3. I'm going to compare 1 and 2 first. Okay, so 1 and 2. In 1, the normal is 3 comma negative 2. In 2, the normal is 6 comma negative 4. We know that they are scalar multiples of each other. n2 is twice n1. So we write that down. n2 equals 2 times n1. Okay? That means that the normals are parallel. Okay, if the normals are parallel, then so are the lines, because the normals are rotated from the line by 90 degrees for each one, so the same amount. Okay, so this is really the picture that you get right here. You've got the 2 lines, and their normals are parallel, then the lines are parallel. Okay. Now, if we compare 1 and 3, compare 1 and 3, go down here, n1 equals 3 negative 2, n3 equals 2, 3. Their slopes are flipped and one negative. It's like we've done the negative reciprocal like we do in equations of lines. Perpendicular line to another has a slope that's the negative reciprocal of the other. So flip the 2 and make one the opposite sign. That's what we've done here. Okay. So if you do the dot product of these 2, you're going to get 0. They are perpendicular. So the normals are perpendicular, which means that the lines must be perpendicular for the same reason as before. Okay? And then we have this conclusion here. So if we have, there's line 1, there's line 2, the normals are perpendicular, implies that the lines are perpendicular. Okay, and so our final statement would be 1 is parallel to 2, and 1 and 2 are perpendicular to 3. Okay, and that's it for that.